So let me start this class, the one before the last. It's about deep networks, and it's about a dynamical system approach, trying to understand what happens when you train a deep networks and what the weights converge during training. As you know, what you have typically is that you're taking the gradients of the gradient with respect to the weights of the loss function. So this will be something like minus dl dvk ij, where w k is the matrix of weights at layer k, and ij are the particular element in the matrix, particular weight. And so this is the doing gradient descent. I'm skipping in this continuous approximation details like the learning rate gamma. I would say something next week about it. But just looking at the gradient flow that is induced by minimization by gradient descent. So the change in time of the weights. And so first of all, it's important to realize that if you consider networks with RLU, then you have networks that in a certain sense are similar or share some properties with linear networks because of the RLU. So for instance, if you take, if I take the derivative of the RLU, let's call it sigma, with respect to z, I get z. This is the same as if I'll take the derivative of just z with respect, multiplied by z here. Okay, and and there are interesting properties that we'll use because of this called homogeneity of the RLU function. As we saw already previous times, the network itself would be a function of the input x, and it would be a series of matrix weights. So this will be the last layer, capital K, and then this will be multiplied component-wise for the lower layer. All of this will be ij and so on, and until you have W1 is the first layer, and this is you'll have this kind of expression for the deep networks. Now, because of the RLU, I can really define an alternative way to write the network, which is given here. I call W tilde here, which later I'll call this VK. This will be the matrix at layer K, normalized by the Frobenius norm of the matrix at layer K. So you know what the Frobenius norm, I could choose another one, but just for simplicity, is square root sum of the squares of the matrix. It's a positive number for each layer, And so because of the RLU, if I multiply or divide by a positive number the matrix at one layer, the output of the network will be multiplied or divided by the same number. Because if you have the RLU of some x, if I multiply x by a positive number a of x, so I have a of x, this is the same as a times the RLU of x, okay? So let me, if I define by rho k the norm of the matrix of each layer, the Frobenius norm, then I can, let me do this because I'll use this later. I'll define the normalized weight matrix layer k. This will be the old one divided by rho k. Is all clear? Okay. So there is also this other interesting property in a paper by Sasha, which is that if I consider now the matrix W as vectors, so lexicographic order, for instance, then let me write it for now like this. It's the sum over ij of wk ij, the derivative of f with respect to the same wk ij, is equal to f of x. And being careful, because sometimes I treat the w as matrices and sometimes as vectors. In this case, it should be vectors. I can write this, if I consider as vector, as a dot product of the vector wkij and the derivative. Okay. So the main point so far is this one, that I can write the network in terms of a normalized network f tilde, where all the matrices are normalized by the Frobenius norm there, and I take the norm outside. And so I can call rho the products of the norms. All right, now let's go back to gradient descent. And of course there is I could do gradient descent on the square loss. In a general problem, we are very interested in the stationary point of gradient descents when the W stops changing, at which point, if it does, at which point usually you stop. The system, the dynamical system has converged. And then looking at the stationary point, whether you have a minimum or a saddle or a maximum, or and it's stable or not. But and we'll see later, stability, for instance, is can look at it looking at the Hessian of the loss function at the equilibrium point where W dot is 0, and typically for a stable equilibrium point, when the Hessian is negative definite, you have a stable minimum like this, but in many dimensions. Okay. If you have a flat one, will be a degenerate minimum. The Hessian will have 0 eigenvalues, and so there are all these questions: do we converge? Which kind of convergent? Which kind of stationary points will we have? The kind of there's been in the last year or so quite a bit of activity of people looking at deep networks under the square loss for instance, results like the neural tangent kernel and so on. But today I'm going to speak mostly about exponential type losses. These are the ones that are used mostly in practice when you have to do classification. So typically, I don't know, I assume you use deep networks, you know, I assume you use like cross entropy, is that correct? Right, so those exponential type losses like the cross entropy are ideally suited for classification problem, binary or multi-class. Here I'm not using the cross entropy, I'm using a simplified version of it, but as far as I know, all of the properties we'll discuss essentially are true also for the cross entropy, or the logistic, which is the special case of the cross entropy for a binary classification. So the loss function will be e to the minus yf, and I'm considering for simplicity binary classification, so y, which is the label, is +1 or -1, and f is the neural network. And so in order to have a small loss, I would like to have yi and f of xi have the same sign, because then the exponent will be negative, and this thing would be small. If the signs are different, then there is a minus in front, you have a positive exponent, you have e to a positive exponent, this can blow up. So the goal here is, you see here that by minimizing this loss over the training set, you are trying to find parameter of f. Of course, you're minimizing with respect to the weights which are inside f, such that, as a first step, such that the signs are correct with the examples, so that your loss on the training set is small. And in fact, if you have more parameters than data, you know, it's kind of intuitive that you can more or less always find an f that fits. In this sense, fitting means has the same sign, the correct sign, same sign as yi for all the n example yi. Okay. So, for instance, the simplest case is the linear case. This is a linear network, one layer, and in this case, the dynamical system that I get, just following the same recipe, is the gradient of the sum of the Li, and this will be minus and minus will become plus, is sum over the training set of this exponential time the components j of the examples. Okay. Sorry?
Why do you consider this dynamical system?
Well, this is what happens if I train a linear network on that kind of loss. This is a special, just an example. If I have a linear network, sorry?
You are considering the continuous version of gradient descent?
Yeah. I'm considering what is called gradient flow. Yeah. I'm considering the...
And you want to like analyze like a curve on this gradient?
Well, there are a lot of tools in dynamical system, especially gradient dynamical system, meaning continuous ones, where you can explore you know, properties of the dynamical system itself. Later you may want to look what the discretization has as an effect, in which direction. The basic intuition, if the learning rate is small and is decaying, as you should do, then you're approximating the behavior of a continuous gradient flow. And so in vector notation, what is here would be that, and you can see that that essentially what happens in this case, consider, I mean, the extreme case, you have only one data point, so you have one x, and then suppose, for instance, that WTX is positive, so there you have a negative, but you have a sum of positive or negative. The sum actually disappears. There is only one element depending on x, whether its components are positive or negative. This will grow or decay all the time, so it will never converge to a finite value. We'll see that in a second, and this is empirically what you find when you train. The weights grow, the norm of the weights continues to grow for as long as you continue gradient descent. So so for instance, I can rewrite everything I wrote so far, but in terms of particularly, let's write the loss function in terms of f tilde and rho. So instead of w, I have normalized, as I shown before, the f, each weights matrix, and I took out the rho. Okay, it's just the same function, only that now instead of a set of w variables, I have v variables, the normalized weights, and the rho 1, rho 2, rho 3. Okay, so now this you can, for instance, say, suppose I want to minimize L, and say I want to minimize with respect to V and rho, right? Because I essentially change variables from W to rho and V. So I'm doing this just to show one thing, is that if I do if I write, say, rho dot, this will be, if I can use the usual gradient descent, will be dl d rho, and this would be the sum, and then I have e to the minus n rho f tilde, and then I have yn f tilde here. Okay, and this would be xn, sum over n. Okay, let me make now this assumption that I'm going to make in a lot of these things, and it is that at some point during gradient descent, the gradient descent finds weights such that yn f of xn have the same sign. So in other, this is called separability. Say it again.
Can you explicitly repeat what is the definition of this rho tilde?
F tilde? Well, F tilde is the same. Remember that we had Yeah. So f is this, and f tilde is equal to vk 1m sigma v2 v1 v1 ij xj. Oh. So the only thing that changes is they replace the weights by the normalized version. For instance, vkij will be equal to wijk divided by the norm of wk. It's a Frobenius norm. Is that clear? So it's like I have a network now where the weights at each layer, the norm is 1. If I take the sum of the square is 1. And the only thing that I change is that I have to take this rho, and then it's equal to f. So what I'm saying here is that if you, so it's really like a change of variables, and if I do this, this derivative here with respect to rho, you see the same thing I said before. Rho dot, if you have separability, so yn f of xn is positive, same sign, then this will be small but a positive quantity, and this will be positive. Okay, so this whole thing is positive. So rho dot is positive, or greater or equal 0, and so rho will continue to grow all the time. So the norm of the weights grows all the time. Which is, I'm sure, what you find, right, when you run. Is that correct? Did anybody find weights that become smaller as you continue gradient descent? Okay, so now, to understand what's going on, let's consider the following. There is the kind of puzzle here is that you have these gradient descent equations. As we saw, there is they are not even bounded in terms of the norm. And we also know from everything we saw in this course that in order to have a good behavior of a learning system, essentially able to predict, you need to have some control of complexity. You know, we spoke about Rademacher number, we spoke a lot about regularization, and we spoke about stability. I'll put all of these things together next week, but the important question here is that you need a complexity control in order to have a system that can predict and not just overfit the data. Okay. So, and of course, we know that the key part is not the number of parameters, but is more the norm of the parameter, or some norm of the parameters, in terms of measuring complexity. And just very intuitively, it's a little bit like if you have large parameter values, you know, the number is important, but you can pack a lot of information in large values, a lot of bits. So in a sense, with the norm, you're measuring the information content of the bits as opposed to just a number, which may be misleading. Anyway, that's just an intuition. So the question, anyway, is we have seen, you know, explicit capacity control through regularization terms. We have seen also implicit ones, for instance, I'll come back to this at the end of today. You have seen implicit regularization by gradient descent. Gradient descent is the iteration of gradient descent behaving like a regularization term. I'll show you what Lorenzo spoke about. What I'm going to tell you today is something a bit similar, is essentially trying to ask the question, where is capacity control in deep networks? Because if you look at these equations, like the W dot K and so on, you don't see it. Okay? As I said, the weights are even unbounded, so there is no control of their norm. Okay, so in order to do that, let me consider a slightly different optimization problem. So instead of minimizing just the exponential loss, I'm minimizing the exponential loss. I'm not saying that the V in F tilde are norm 1, as I said before, but I impose norm 1 of the V through a Lagrange multiplier term. Okay? So this is constrained optimization. And that, in a sense, would be what, if you believe in capacity control regularization, what you probably should do anyway. But that's not the way, neural network do it, apparently. So, but let's see what happens with this. We assume, I assume as before that at some point during gradient descent, you have separability. So for all your data point, f of x and yn is greater than 0. So they have the same sign. So this is like saying I have a classifier which already separates correctly the minus point from the plus point, the cats from the dogs. I want to know what happens next. And assuming this separability seems to be a big hypothesis. In fact, in general it is, if you have fewer parameters than data. But if you have more parameters than data, as is typically the case, it's not such a big assumption. Okay. This means essentially also that you find, after a certain time, you find 0 error, classification error on the training set. That's what separability is. Okay, so anyway, let's see what happens if I do this. If I take this Lagrange multiplier term, I want to impose that the VK are equal 1, the norm. And let's see what happens first with fixed rho. And with fixed rho, I just take the derivative with respect to Vk. I get some relatively simple equations. I have 2 lambda k Vk. And I can actually eliminate lambda by finding the by imposing the condition that Vk, the norm, is 1, because I know that if the norm of Vk is 1, then the time derivative of this should be 0, right, because it's constant. And then I also, taking the derivative, I have this. So I can multiply on the left this Vk dot time derivative by Vk transpose. I know that would I can then put it to 0, and I get this equation here, with a lambda, and then this would be 1, and then I can solve for lambda, and I find this equation, and
Why is it 1?
why?
Why is it 1? V transpose V.
This is my condition at the beginning, right? I decide this is the Lagrange multiplier. I want to impose this condition on the Vk. So this equal 1 means Vk transpose Vk equal 1.
I mean, you are considering Vk in your loss explicitly, so we don't have the condition. Normal Vk.
So there are Vk, but they are not. The Vk in the F tilde, I don't say what they are. They're just matrices.
But I mean, their norm is not 1.
Maybe not 1, but
So
I.
how do you
Because I want to impose this, basically, I want to find, I say if I have the correct lambda, it will make Vk equal 1. And I pose that condition and find which lambda does make Vk squared, the norm of Vk equal 1. Let's see. You know, I use I want to find lambda such that the derivative of this is 0 because it should be 1, and I use the fact that V transpose V is 1. And then I find this, that lambda k, in order to satisfy these constraints, has to be this. You can plug it back and check that.
just that you are assuming that the normal Vk is 1.
Sorry?
You're assuming that the normal V is 1.
I impose this as a constraint during optimization.
You also consider it in your loss function.
In my loss function, there is no explicit. I should have changed, you know, to be clearer. These are not the same V that I used before when I said they have norm 1. They are just V. I want to have F parameterized by V and rho, and I want to have the V, because of this term there, to converge to norm 1. This is a typical thing that you can do in constrained optimization. This is one of at least 4 techniques in which you can do optimization, so minimization, while you impose a constraint of norm 1. I can show you other 3, but that's probably the simplest one, Lagrange multiplier. Yeah. Yeah, it does not change once you take the derivative, but
I guess his question is, you seem to be using the norm 1 in this proof,
yeah.
but you did not constrain it.
Well, it's I say here. Yes, because I use that to find lambda. I use exactly this constraint in order to find lambda. You know, I do. It's nice that it comes out so simple. Is I have the equation V dot. There is lambda. I know that the time derivative of V square has to be 0 if that constraint is correct, because it's equal 1. And then I just multiply on the left the equation by V k transpose. I get this, and I solve imposing again the constraint, the Vt v equal 1. And I get a certain value of lambda that I plug back in. So I've used the constraint Vk norm 1. Sorry?
The logic is that if you plug in lambda, if you plug in norm 1 and then solve for lambda, it's not obviously the same as it's in the wrong direction, right? Like it could be that with that lambda you get norms other than 1.
I don't think so. It's not a traditional way to do Lagrange multiplier, but there are a couple of ways to do this. One is Amari, in which it computes the squares and so on, but this is a simpler, more elegant way. And so you get this equation for V for fixed rho. So for a fixed norm, if you can do gradient descent only on V, you stop growing the norm of the weights, you get that equation. And it's interesting that now you have a part of the equation, that one among parentheses, that could be 0 at some point. So if you look at the W, they will grow all the time. They will never stop changing in time. But here, if you look at the V, the dynamics of the normalized weights, if this term in parentheses become 0, you have a stationary point. The question is, when can that happen? First of all, we are in a compact domain because this is Vk is on the sphere, and so I know there is at least one minimum and maximum, of course, with V dot k equals 0. We have also, if I have time, I'll do it next week. You can compute the Hessian for a fixed rho and find that at the equilibria, if they exist, the Hessian is negative definite. Okay. And we have some computational experiment I'll show you next week showing this. So just to, I'll say something more in a moment, but the landscape looks like it is, for a fixed rho, you have many valleys, each one roughly corresponding to a different support vector, or for a different group of inputs. And these are valleys that become shallower and shallower as the rho becomes larger. But each one is a stable, so-called hyperbolic minimum. If you perturb the weights during gradient descent, this is something we have done, you can show that if the perturbation is big enough, you jump from one minimum to another one. Perturbation is small, you change, but then come back to the same minimum. So it's you're really in, seen at a constant rho, you have a profile like this. So you may be here, and if you perturb, you may jump to another one. If you perturb only a little bit, you come back. but let me first. So first, let's see what happens when rho goes to infinity. Essentially, going with rho to infinity in the previous equation, it was for fixed rho. I can just take rho to infinity in these equations here. So this is the equation. I can take rho to infinity, and of course rho will go to infinity, but this will dominate, so eventually everything is going exponentially to 0. Will never be exactly 0 unless this becomes 0 at some finite time. Okay, and if you take rho to infinity, rho is only here, it will not affect that part. And this is the same as considering the full dynamics. So suppose I'm taking the derivatives not for fixed rho, only respect to v, like I did, but I take it now with respect to v and rho, right? From the same Lagrangian. And then since rho dot increases monotonically, is essentially equivalent to take the limit for time going to infinity. So rho to infinity and time going to infinity are equivalent. So you can show that both those limits for rho going to infinity or for t going to infinity, when you have the dynamics of v and rho, they converge to maximum margin. So you define margin as of a function f tilde, like eta, which is the minimum over all the training example of f tilde. That's sometimes called the functional margin. And the intuition is that when you have rho going to infinity or time going to infinity, you have the sum of exponential rho f xn. The one, they will go to 0 essentially, and the ones will go to 0 faster are the f tilde, which largest value. If a certain x1 has f tilde x1 is large, then this term will go fast. The one corresponding to eta is the one which is going to 0 the slowest. So if you wait long enough, there will be one term surviving among all the exponentials. And this will be that one corresponding to the xn, or a group of xn with the minimum value of f tilde. So what happens is that instead of having this sum of the exponential and this parenthesis df, you now have only one term at some point. And then you can see that the exponential term can be very small, but non-zero. But if this other term is 0, then you have converged. And so the condition for convergence is the f tilde dvk equal this. And the convergence will be to the maximum margin. This equation, just as an example, suppose I take f being linear, then that equation there tells me that you know, if I have vtx, like my function is a linear function, v transpose x, derivative v, I have x, support vector, and then I have vtx v. This is the equation for the linear case, which gives me that it converges to a vector of weights that is identical to the support vector. And that's a very much simpler way to derive this than other ones. So now, okay. Now the main point is to, we have, here we saw constrained normalization, constrained gradient descent. That's not what deep networks do. Right? So let's look at the unconstrained one. So what everybody does with deep networks. So in this case, again, these are the same equations. What I want to do is a change of variables. And so I want to define this normalized matrices, considering them as vector. So V would be, as I wrote before, this is in the linear case, W and divided by the norm of W. This W tilde is actually V. Let me see. And if you work out this various definition is a little bit painful, but you can see this basic relation that the derivative of the norm of W with respect to W is equal V, and the derivative of V with respect to W has this particular structure, term S divided by rho. Okay, this is just work that needs to be done, because then what I want to do is to take the standard equation that people use in the W and make this change of variables. Replace you know, V with rho and a normalized V. This small V. And then see how the dynamics of W, which kind of dynamics is induced on the normalized ones. And it turns out, yep. You want here? What is it?
What is S?
Oh, S is the identity matrix minus V transpose.
Oh, you define it.
It's defined, yeah. And rho.
You're taking derivative of
V with respect to W. I need this derivative when I want to make this change of variables. That's why I write.
V and W are both matrices, right?
They are, I consider them as vectors in this case. So for simplicity, think of the linear network.
Okay, I mean, like the derivative should be like a cube, right?
Well,
It should not be a matrix. I'm confused, but it's
you know, you have the derivative of a vector dv with respect to another vector w. So in general, you get a tensor out. That's what you get, is a matrix, a tensor of order 2.
Yeah, so I here is has like
Identity?
if V is if you consider V as a vector and it's like n dimensional, I is n by n.
Yeah. S is actually what is called a projector, and we see that in a moment is so. So I want to go from this equation, which is the usual one, to one in terms of these new variables. And you know, without going through the steps, if you want, I can do it next time. But I get what I do is I compute. I use the chain rule, so. Rho dot k will be the rho the w, and then the w the t. And the w the t is the equation I've just shown before, right? The one that everybody is using. What I need to know is the rho the w is one of these things that I wrote before. You know, is that is the derivative of the norm of w relative to w. It's this one. So the rho k, the wk is this one. Because rho k is the norm of w. And dwk dt is, of course, this. So if once I have that, I can compute the dynamical systems for rho k and vk. For vk is the same chain rule. And what I get is for rho dot is rho over rho k, and then that sum, and again this will be positive under separability, and therefore rho will continuously increase. And vk will be this thing here, and you have this term rho over rho square k. So if now I compare this with the constraint, the gradient descent, the one with the Lagrange multiplier, I find that they're very similar. The rho equations are the same. The v equations are exactly the same, apart from the fact that in the constraint case with the Lagrange multiplier, I have a rho term here, and now I have a rho divided rho square k. But they're both positive. So since they're positive number, when I want to find when v dot k is 0, it will be the same in both cases. So what I'm saying is that the dynamics of the constraint case, in which I have a Lagrange multiplier, a kind of regularization term, and the case in which I don't, the case that people use, have the same stationary points and a very similar dynamics. Yeah, let me. So you already saw a lot of things. Let me make, yeah.
So the distinction between constrained and unconstrained is kind of artificial, right? Because even in the constrained case, you just pulled out rho, and so what remains by definition would be of norm 1.
Well, in the, maybe one should use, I should use different notations, but in the case with the Lagrange multiplier, I assume, I take out rho, I can always do that. But the V could be not norm 1, or not remain norm 1 during gradient descent. So I don't impose to be norm 1 in the constraint case. I impose it through the Lagrange multiplier. In the unconstrained case, the unconstrained case is like saying, so this is like saying I impose the norm 1 during minimization, I get some results. This would be the standard way to do it in one case. The other case is I don't impose that constraint, but what I use at the end, when I have the W at the end, I don't actually use the W, I use the normalized version. I normalize after I stop gradient descent. And the results are essentially the same in these two cases, which is a little bit surprising, or not, depending on the points of view. But the interesting, so I don't need here, in fact, to go through the constraint case. I could make the whole argument through the unconstrained case. But I wanted to clarify that the convergence is the same, that is to the same points that I would have if I have regularization and capacity control. So there is like a hidden or implicit capacity control, even if there is no explicit regularization term. And I think that's new. Okay, let me make this quick point about the connection between maximum margin and minimum norm. So this is rather in general. If you have a neural network function, it has this homogeneous property. So a positive alpha can be taken out of the weights in front of f. We are dealing with binary classification. We assume separability. And the max margin problem will say I'm looking for the margin, the minimum over n of this number. And then I take the maximum over weights. This is the, and I do that subject to the norm of the weights being 1. Otherwise, this will have no sense. So the result is that this problem is equivalent to minimizing the norm of W subject to the margin being greater or equal 1. It's something usually one can prove with support vector machines. This is a little bit more general, and make a correspondence between maximum margin and minimum norm, which is interesting for various reasons, one of which is that a big role in many of the things we discussed about, and probably in understanding neural network, is the pseudo-inverse. And there, the pseudo-inverse is really defined in the over-parametrized case as among all the infinite number of inverses of solutions that you have, the one with minimum norm. Okay. So in this case, minimum norm here plays a role which is very closely connected to capacity control. Sorry? You mean in the neural networks? I think would be the role. I did. Sorry?
The product of the Euclidean norms?
Yeah. But I don't know. That's an.
That's
Yeah.
not the norm.
Hmm?
That's not the norm. The product is the norm.
Yeah, I'm not sure this has to be a norm. Yeah, to be honest, I don't know about the nonlinear case because what you can apply this kind of result is to each layer separately. So, summarizing some of the things I said, if you assume all I said is for exponential loss, and very likely it works for logistic and cross entropy, but I don't think it works the way it is for square loss. By the way, how many of you has used the deep network with square loss? Okay, which kind of problems? Sorry?
Learning models for
For dynamical system.
where you want to match the state, you want the learning model to match the state exactly.
Okay, this was a deep model.
Trying it for the project.
Okay.
Not working that well.
Oh, okay.
Yeah,
Well,
he's the same starting trying to use it. It's not working well and trickling.
I'm still trying to find an example where deep networks are very successful with square loss. And yep. Sorry?
Regression problems in general?
Well, yeah, but which one? I know that would be the, but I can tell you ImageNet was a big success, right? I don't have. I'm sure there must be maybe GANs. Hmm?
What are your thoughts about why the square loss makes it difficult?
No, it's actually, well, I don't know. Empirically, we found that it's more difficult to get convergence. For instance, for CIFAR, you can get convergence with the square loss, where you have, it's classification. So you do regression on plus one plus some labels. In that case, you can get convergence, but it's painful. It's a lot of trials, does not work very well.
But for that application, for classification, like the square loss really doesn't make sense as opposed to some of these other losses.
Yeah, that's
Application that's naturally a regression.
yeah, that's true. But on the other hand, back 20 years ago, I had a student, Ryan Rifkin. Do you remember? Who is now high up at Google, and in his thesis is compared. I think was the SVM loss, so the hinge loss, with square loss, mostly on, I think, classification problem. And he found out that, basically they were the same. There were some problems where the square loss was better and some problems where the hinge loss was better. A bit counterintuitive because, so I don't know. Yeah, the other point which is related more to what I spoke about the last class is do we have a real success story of deep networks that are not convolutional? Because if we don't, then maybe that what is really important in those problems where convolution works is the architecture. And it's not so important whether you're using an RLU or whatever, or a kernel in its various stages.
Weren't RNNs like a pretty, they were
Sorry,
early,
RNN?
recurrent neural networks were like an early success with language processing. I know now people use convolutions.
They use convolution.
It's kind of just easier, I think, to apply convolutions to do code.
Yeah. But they are convolutional, right?
Right, in some
Yeah.
sense.
Now the question is, there are certain type of problems where you essentially you can think of the problem as naturally being decomposable in parts and objects, and so a hierarchical way. Those problems are really like text, letters, words, sentences, speech, same, images, objects, and but if you take, for instance, a finance problem, clearly the type of homogeneous, regular, convolutional architecture, I'll be very surprised if you do. By the way, it would be interesting problems I mentioned last time, to think of architecture that could be compositional, but where the graph structure is different. And there might, especially fought for certain classes of problems. For instance, in finance, you may want to group together, I don't know, financial instruments of the same type, or like bonds versus stocks, or geographically. So there will be some composition, but it will not be composition, regular composition, like convolutional networks. So I was saying, so then what we, under those assumptions, we can show that gradient descent converges to a minimum norm solution in terms of the weights, each of the weights. And the solution has this hidden regularization, is the same as if you have the constraint problem, essentially because of the normalization. And these are kind of some of a list of the other results that we looked to, like the limits are the same for t or rho going to infinity. The limit is the maximum margin. The dynamics of the constraint and constraint are slightly different, but the convergence points are the same. One of the more interesting things is, I hope I'll show you some images next week, is that the convergence for any finite time is to a hyperbolic stable minimum. It's one of the support vectors. And you're there, stuck there. If you wait for infinite time, your hyperbolic minimum is becoming flatter and flatter and flatter, at infinity is totally flat, so it's degenerate. There are a few other things. For instance, what is called weight normalization, which is one technique you probably know. It's closely related, but it's not the same as batch normalization, which is probably even more useful. But those correspond to the constraint problems. The way they are formulated essentially correspond to the constraint problem. So that does not change the asymptotic convergence points. The dynamics is slightly different. For instance, in the linear case, we can prove, this is a very simplified case, so don't take it too seriously, but weight normalization converges much faster than the normal gradient descent. Another thing that I don't know if you have ever looked, but how the norm of each layer grows. It should grow at the same rate, independently of the layer. So in particular, more specifically, the time derivative of rho square k, this is Frobenius norm at layer k square, is the same independently of k. It's kind of interesting. And they should basically grow, it's something like log of t, roughly. For one layer network is exactly log of t. For more layer, it's a little bit faster, but each layer is a bit slower and so on. Yeah. So, so the main point I wanted to make is this hidden regularization. And as I said, this is a bit similar for the exponential loss and for general deep networks. It's a bit similar to this result that Lorenzo spoke about for linear networks and square loss, which is this story that you have in his notes, that if you, because of iterative gradient descent, you are converging to a minimum norm solution, as if you have a regularization term that goes to zero. Now this is true for the square loss and for linear networks, and furthermore requires your initial condition to be zero. So you have to start to very small weights in order for this to be true. The result I showed is true for exponential loss, not square, but it's true for nonlinear networks, multi-layer, and it does not depend on initial condition, so it's much more robust. You'll converge to this maximum margin independent of initial conditions. Okay. So, again, the main message to take home is this one, that there is complexity control in deep networks, despite the fact that it does not look like they have it. And this does not yet explain all the properties of deep networks, like good performance for over-parameterization. But I'll tell you next week, there are some intriguing properties, actually, of systems of linear equations that have to do with that condition number of system of linear equations, which is something I find very trench that people don't know it yet. So we'll speak about it, and that has more directly to do with the overparameterization question. Thank you.